All right, so today we're going to talk about weak bases. Okay, we talked about weak acids last time. Now we'll be discussing weak base. So just a reminder, what's the difference? Acids donate, right? Whereas bases accept. So the way we write our general formula is going to be different for an acid than it will for a base, right? Because when we did our weak acid or strong acid calculations too, when we did calculations involving acids, we were looking at something that's donating H+, whereas with a base, we're looking at something that's accepting it. Okay, so just make sure that you're looking at a base differently than the way you're looking at an acid. Reminder, this is a figure that we saw earlier when we first started talking about acids and bases. Fundamental difference between the acid and the base, right? The acid is the H+ donor. The base is the acceptor. So a base needs to have a place for that H+ to go, right? Bases need to have a lone pair. They need to have somewhere where that H+ can be accepted. So one of the things that a lot of students come in with as a misconception is they think, oh, all bases must have OH in their formula. That's something that a lot of students think. If it doesn't have OH in the formula, it can't be a base. That's something that you see a lot in high school because most high schools at the introductory level don't go real great into detail about acids and bases, and that's fine. But a base does not have to have an OH group, okay? A base is any substance that can accept H+, and then it also produces OH-. But it's not the base that's producing the OH. Who's producing the OH? Where's the OH coming from? It's not from the base, it's coming from the water, right? Because this is the generic formula for a base, any base. You're going to have your base plus water Look, the water is donating here. The water is acting as an acid, okay? And the OH- isn't coming from the OH. I mean, the OH- isn't coming from the base. It's coming from the water, right? So when you were in high school, you probably learned bases produce OH-, and that's true, but technically, it's not the base itself that produces OH-, it's the water, okay? The conjugate base of H2O is OH-. That's what's producing the OH-, okay? So I want to clear that up. That's a really common misconception because a lot of times students come in thinking all bases have to have OH in their formula so that they can produce OH- when they dissociate. But when you think about it, water's acting as an acid here, and the OH- is just its conjugate base. That's what's producing the OH-, okay? So by definition, any base is just something that's got a lone pair of electrons that can accept H+. Do we understand this definition? Okay? The way we think about a base is different than the way we think about an acid. Just because we're looking at something that's a donor when we're looking at acids, but we're looking at something that accepts when we're looking at bases. Okay, so this is the example I just showed you over here. NH3 was the example. All right, so this is the generic formula. You need to know this. I just wrote it on the board. All right, you've got to know this. Any generic base plus water's acting as the acid, will produce the conjugate acid and the conjugate base. Again, this is where your OH- is coming from. So any base has the generic reaction like this. All right, we have the general reaction for an acid. Now here's the general reaction for a base. So you've got to know this. Please put a big star in your notes. Memorize this. It's really important, okay? You need to know the generic reaction for a base with water. And just like with our generic reaction for acids, right, H2O is a liquid, so will it be part of our ice table? No, it's not going to be part of the ice table. Does everybody understand how bases react compared to acids? How they look? They just look a little bit different But we're still going to set up an ice table, right? A weak base is still going to be strongly reactant favored. So our need for an ice table has not gone away. So I'm going to pause this for a second, give you a chance to try these. Write the dissociation reaction for each of these bases. Let's look at the answers here for our dissociation reactions. So if this is our base, right, AQ, plus H2O, what's going to happen to it in terms of number of hydrogens? Is it going to go up or go down? It's going to go up, right? Because this is donating H+. So what's the formula over here? CH3, NH3. Is there a charge? Yes. Right. And then what's our other product? OH minus. Now we can write an equilibrium expression for this. We wrote Ka for acid, so what do you think it's going to be for a base? It would be Kb. Right, so Kb is just going to be the same way we wrote Ka, products over reactants. All right, and then using our initial substance. So the equilibrium expression for a base is called Kb. Equilibrium expression for a Ka would be for an acid. Now for a strong base, would you expect Ka to be greater than 1, excuse me, Kb to be greater than 1 or less than 1? Weak base, right. Kb is less than 1, right? And remember, there are only 3 strong bases that you're responsible for identifying, so we're assuming all the other ones are weak. Let's do this one. AQ, we're combining that with H2O, liquid. That's in equilibrium. What happens to my formula here? Add into H what? 5 plus, good. AQ plus OH minus. And so the Kb expression here would be N2H5 plus times hydroxide over hydrazine N2H4. Just like with acids, we omit the H2O, right, because it's the liquid. Be cool on how to do dissociation and write a Kb. Okay, it's just a little bit different from an acid. In terms of the calculations, it's no more difficult because you're still going to be doing an ice table, and then all the stuff we did last time with percent dissociation, all that stuff's exactly the same. It works out the same in both conditions. So it's really no more difficult than acids. Just remember not to confuse acids and bases. I can't tell you the number of times when I mark students wrong for writing their dissociation because they treat a base like an acid. And they'll write base produces H3O+. And that doesn't make sense, right? Because the base can't produce H3O+. That's just not possible. So make sure you're treating your base as a conjugate acid and hydroxide ion. Don't write this and then switch up to this. That would not make sense. Okay? Don't treat your base like an acid. And so there's our Kb expression. And then Kb will be less than 1 for a weak base, right? And if you need a Kb value, that appendix at the back of your textbook, where the Ka values are on the page right beside it, will be the Kb values. On your exam, I will give you a reference page with Kb values if you need one. Okay, so I'm not asking you to memorize Kb values. That's just insane. Now remember, we did strong bases already, so now we're doing weak bases. So let's do this one together. What is the pH of a 0.15 molar ammonia solution? Its Kb is 1.8 times 10 to the negative 5th. So we're going to do ice table, just like we did with weak acids. And there's only one little twist that's different. It's just one tiny modification that makes the base different from the acid in terms of what we're going to do to get pH. So first thing we have to do is what? We have to write the dissociation, right? So dissociation equation, remember this is a base, it's accepting H plus now, so you're going to get the ammonium ion and hydroxide ion. To get Kb, that would just be products over reactants, right? No H2O. So that part we already covered, writing your dissociation. Now when we make our ice table, we're going to make the 5% approximation. Why? Kb is less than 1, right? So the problem told me it was 0.15 molar to begin with. So it's going down by x. So we're assuming that x is so small that it's not going to be a huge impact at equilibrium. These two values are initially 0. They're going to go up by some quantity x. Okay, so we're doing the exact same setup in terms of our ice table as we did with weak acids. Everybody cool on how we did this so far? All right, now we're just going to solve for x. So we plug in our Kb value. X times x is x squared. Plug in the 0.15 as the concentration. I came out with 1.6 times 10 to the negative third. So here's where it gets different. Notice, can I calculate a pH from a hydroxide ion concentration? pH is log of H3O plus. Negative log of H2O plus. I've got to calculate pOH first and then convert it to pH. That's the only main difference. All the ice table and the math that's involved with the ice table is exactly the same. But if you were to calculate this negative log, that's not going to be a pH, is it? It's going to be a pOH. So how do you turn a pOH into pH? You just subtract from 14, right? So we have to calculate pOH first and then get pH by subtraction. Okay, so if you stopped right here, you would not have a pH, you would have a pOH. You need to subtract from 14 in order to get a pH. And always ask yourself if your answer makes sense. The pH of a base is going to be greater than 7, right? pH of a base should be greater than 7. If you get a pH of a base and it's 2, that's not a pH. That's got to be a pOH, right? Because bases have pHs greater than 7. So your answer would need to be reasonable. Okay, that should be kind of a self-check there. Does everybody understand how we did this problem? No different than the ice table for the acid. The only difference comes in the final step. We have to calculate a pOH first and then convert that pOH into a pH. Any questions on this? Ready to try one? Oh, just kidding. I have a problem for you to try in a minute. Let's do percent dissociation. So the way we did percent dissociation for an acid was H3O plus at equilibrium over the initial concentration of the acid. We're just going to substitute in the base analog here. A base doesn't have H3O plus, right? A base has OH minus. And obviously there's no initial acid concentration because it isn't an acid. So in terms of our ice table, right, it's this value divided by this value times 100. Would we expect these values to be big or small for weak bases? Percent dissociation should be, for a weak base, small, right? Because it's reactant favored. The equilibrium's over here, right? So we should expect these values to be really small. For a strong base, they should be really big. For a weak base, they should be really small, right? Because strong bases, we assume 100% dissociation. So why don't you try this one? Calculate the pH of a 1 molar methylamine solution. And here's its Kb. All right, let's see what we got. So we have to write our dissociation equation, and we can use the 5% approximation, right? Because this is a weak base, so we can assume that X is small enough that at equilibrium the value is not essentially going to be any different from the initial. And so we do our math, plugging in our KB, 4.38 times 10 to the negative fourth is equal to X squared over 1. So I got X is equal to 2.1 times 10 to the negative second. And then this value is right here and right here, right? Now, if I take the negative log of this, that's not going to give me pH, is it? It's going to give me POH, right? So the POH is 1.68, but the pH would be 12.32. Do we got it? Get it right? Any questions on this one?
Yeah, so why is it, so for the molarity, it's only 2 sig figs. Why is that down there? The final answer.
So we have 2 sig figs here,
Yeah.
so that means we need 2 decimal places in here. And then when we subtract, we go by decimal places again. Because we're assuming that this value's got 2 decimal places. Does that make sense? We're going by 2 sig figs here, so we get 2 decimal places here. And then we're treating this like a constant with 2 decimal places. And sig fig rules for subtraction are going by decimal places. So that's why there are 2 decimal places here. Yep. That's the one thing that gets kind of funky, right? That's the big difference in sig figs for logarithms. All right, why don't you try this one? You've got a hydrazine solution, and there's its Kb, and you know that its molarity is 0.25 moles per liter. I want to know the pH, and I want to know percent dissociation. And just FYI, if you ever see percent ionization, it's the same word, so don't let that throw you off if you see it in your homework or if you're reading online or whatever, right? Percent ionization, it's the same thing as percent dissociation. Let's try this one. All right, let's see what we got. So we have to write our dissociation equation. We have to make our ice table, right? That's what our ice table looks like. And so I got X is 4.9 times 10 to the negative fourth. Did you? And so that gives me a POH, which I then convert to a pH. Can we agree on these 2 values? And now for the percent dissociation, that's just the amount of this at equilibrium divided by the amount I had initially, right? And so of this 0.25 moles per liter, only this 4.9 times 10 to the negative fourth actually dissociated, right? So 0.2%, is that a reasonable percent dissociation for a weak base? Yeah, especially given what the Kb is, right? That's a really small Kb, so you would expect that to be a pretty small percent dissociation as well. All right, if you come up with, 150, that's not reasonable, right? Because this is a weak base. So if you have a very big number for your percent dissociation, you either flip something here or you need to go back and double check your math here. Do you feel good about this one? Feel good? All right, this is the last one for today. Methylamine stinks, doesn't smell very pleasant. You have a 0.1 molar solution and you find that only 6.4% is dissociated. So I want to know what's the Kb and I want to know what's the pKb. See if you can figure this one out. All right, last problem. So I've told you that you do an experiment, you find it's 6.4% dissociated, and I want to know Kb and pKb. So we have our dissociation equation, right? And that's what we would write for Kb. And this is just a formula for percent dissociation, right? It's the amount of hydroxide at an equilibrium divided by, whoops, that's the wrong spot. That's in the wrong, I copied and pasted the wrong thing. That should be this. There we go. Copy and paste. Copied the wrong thing. Okay. And I put it right there too, didn't I? There we go. So the problem told me it was 6.4% dissociated, right? Because this is times 100, don't forget that how do you undo the times 100? You take your 6.4 and what? Divide by 100, right? Convert that percent to a decimal. So now all I do is just plug in, right? This goes here. This is what I'm solving for, and this was from the problem. Problem told me it was 0.1 molar. So when I do my arithmetic, I got 6.4 times 10 to the negative third as my value of x. Did you? We agree on x? Now, if you were to make an ice table, which, I mean, I think you can probably just do this in your head. I don't necessarily think you have to write out the ice table, but of course you're welcome to. Right? If you were to make an ice table for this, this is what it would look like. Right? This is the value of x that we just solved for. But if we were to make an ice table, we would not use the 5% approximation here, right? Because we're solving for KB. So if we approximate the E value, that's going to make our KB value not as accurate, right? So we want to use the exact value of x. We don't want to make the approximation. So to get our KB, I got 4.4 times 10 to the negative fourth. Did you? Do you agree? Do we agree on this value? And then how would I turn that into a PKB? What does P mean? Just take the negative log, right? So I got 3.36. Do we agree here? All right, that's where we're going to stop. So tomorrow we'll be doing some enrichment on all this.